Okay, so hello and welcome to the week 8 tutorial session. And in this tutorial, we're going to cover the topic of the tolerances and fits. So first, we're going to talk about a brief introduction about the tolerances and fits, and mainly about the topic of the stresses analysis or the force fits. Now, you know that what the terms of the tolerance mean is going to be the permissible uh, addition or less value for the dimension during the manufacturing process to be acceptable. Because most of the manufacturing process cannot give you an accurate dimension, and if you need to have a more accurate dimension, you need to do a further processes, more complicated one using high technology, and this will include increase the cost. So, Codifix is about the mating parts. So an example, just a definition about the stress analysis for the force fits. It's, as mentioned earlier, the stresses exist on the surfaces of the mating parts. Just imagine that we're going to have a shaft to go inside the inner ring of the bearing. So if we're going to have a high interference ratio between the shaft and the bearing ring, then we're going to have higher stress to be imposed on both the shaft and the ring, and then the ring will transfer it to the rolling part of the bearing, and this will damage it. So such stresses can cause a failure in brittle materials. Definitely, we're going to have the ring to be made of, for example, cast iron. It will crack. Stress analysis is related to the analysis of the thick-walled cylinders. So the procedure will start first by determining the amount of the interference from the design of the parts. So we need to know what will be the B value and the C value, because these are the two mating parts where the interference will occur. And we will see that if this value for the sigma, delta, sorry, is going to be positive or negative. Usually the inner part is going to be called the pushing and the outer one is going to be called the sleeve. And inside the pushing, we're going to have a rotating shaft, for example. So after we finding the value for the A, B, and the C, go to the tables, find the nominal diameter of, maybe it's going to be the B times 2. We go to the table, we find out what will be the permissible tolerances for that dimension. And once again, we have standards. If you're going to check the video for the lecture, you will find more details about that. Step number 2 is going to be compute the pressure at the mating surface of both members of the same material or different materials. So when we say both are going to have the same material, so the equation, which is that the main equation, is going to be dropped to this part only because the E is going to be the same. A is the elastic modulus of elasticity, P is the pressure at the mating surfaces, and the V over here is the Gaussian ratios that we talked about earlier. The B is the diameter of the radius of the mending part. Same thing is going to be for the C and the A, is the radius of the outer surface uh, for the outer part, and the A is going to be the inner radius of the inner part. So after we finding that, we can simply compute the tensile stress in the outer member and the compressive stress, of course, is going to be on the inner member using the following two equations respectively. Then we can compute, if desired, the increase in the diameter of the outer member due to the tensile stress and the decrease in the diameter of the inner member due to the compressive stress can be computed from the following two equations. Short example on that, we have a bronze bushing is going to be installed into a steel sleeve. So we have two different materials here, as indicated in the figure 13.6. The bushing has an inside diameter of 2 inches and a nominal outside diameter of 2.5 inches. The steel sleeve have a nominal inside diameter of 2.5 inches and the outside diameter of 3.5 inches. Okay, so if I'm going to explain to you what we have here, The 2 is A times 2. The 2.5 is the B times 2. The 3.5 is the C times 2. Okay, so these are the dimensions we're looking at. Now, first I need to specify the limits of the size of the for the outside diameter of the pushing and the inside diameter of the sleeve in order to obtain the heavy dry fit or the FN3, determine the limits of the interference that will result. For the maximum interference from 1, we can compute the pressure and will be developed between the pushing and the sleeves and the stress on the pushing and the sleeves and the deformation of the pushing and the sleeve. We can use the value for the E or the Young modulus of elasticity for the outside part to be 30 times 10 up to the power 6, and for the inner one, which is going to be the bronze, as 17 times 10 up to the power 6 megapascal. And sorry, that's Pascal, which is megapascal in general. For the bronze, use the value for torsion ratio to be 0.275 for both materials. So once again, this is the example just to show you how the stresses are going to work. And the solution will start first by determining the amount of the interference from the design of the part. You go to table 13.4. I'm going to send you a copy of that. From this table, for the part size of 2.5 inches, because that's the diameter we have for the mating surface. So in the table, you can find the nominal basic size, anything between 1.97 to 2.56 is going to have for the FN3. The dimension to be 1.3 and 3.2. That's the max and the minimum, and this is the maximum. So for the hole, which is going to be S7, is going to be 1.2. For the shaft, which is at T6, is going to be 3.2. By the way, these things are the code for the tolerances we're going to have for the shaft and the hole. The hole is going to have a capital letter, and the shaft is going to have a small letter. Anyway, so we got the value from the table as 1.3 and 3.2. So simply we can, for the hole, you can add the value for the diameter. So the minimum value is going to be 2.5 and the maximum diameter is going to be 2.5012. Now, I'm going to remind the interference for the design of the part for the bronze insert, which is going to be the inside one. The limits are going to be 3.2 and 2.5. Then the size limit of the outside diameter of the pushing is going to be 2.5032 and 2.5025. Okay, so now we got the values here and we can continue with our solution. So you can see what we add in here are these values for the shaft part. So by adding 2.5, that's in thousands of the inches. Okay, we can find the minimum diameter here. And by adding the 3.2 divided by 1000, you can find what will be the maximum diameter for the shaft. So the limit interference is going to be equal to 0.0013 to 0.0032 inches. Now, to find these values, we're going to have the maximum and minimum of each one and do the subtraction. So you remember that the minimum diameter we had for the hole was 2.5. So the maximum diameter we have for the shaft is 2.5032. So the 2.5032 minus 2.5 will give you the value for the maximum interference. While the same thing is going to be for the minimum diameter for the shaft minus the maximum diameter of the hole will give you the minimum interference between them. Now we are going to compute the pressure at the mating surface of both members are going to be from different materials. So the maximum pressure will be produced by the maximum interference, which is 0.0032 inches. Then using the A to be 1 inch, the B is 1.25 inch, the C is 1.75 inch, and the elastic modulus of elasticity for the steel to be 30 multiplied by 10 up to 6 psi. And for the bushels, bronze bushel is going to be 17 multiplied by 10 up to 6 psi. And the portion ratio is going to be the same for both, which is 0.27. Of course, portion ratio is unitless. So now we go to the equation. I'm going to substitute the parameters in, okay, and do the calculation. Now, in the book, you may miss this 2 as in the front of the B. I don't know what the reason is, but some of the examples missing this 2 in the front of the B. Now, just substitute everything. The delta was the maximum interference, which is 32 divided by 1,000, and sorry, 3.2 divided by 1,000. And then by applying everything, you will find that the answer will be equal to 3,518 psi. So we finish with the step number 2. We jump to step number 3, which is going to be about calculating the tensile stress in the outer member and the compressive stress in the inner member using the following two equations. The first one is positive because it's going to be compressive. The other one for the inside is going to be compressive. So the first one is tension, the other one is compressive. Compressive negative, the tension is positive. So we start to apply the P that we have calculated, and the diameter that's, sorry, the C value, which are the radius that we got from the first calculation step, and it will come out that for the compressive stress, for tensile stress, we're going to have the value to be equal to 10,846 psi. Now we're going to repeat the same step for the compressive stress on the inner part, and you will find that the answer is going to be equal negative 16,025 psi. Now, step number 4, of course, is going to be about finding the change in the diameter for the outside and the inside one. So the increase in the diameter and the outer member due to tensile stress, and the decrease in the diameter in the inner member for the compressive stress can be computed from the following two equations. So you can see that this equation actually going to be a section of the main equation that we have for the pressure. So we just put everything in. You can see that the whole thing we have here is going to be about multiple diameters and the EO. And we're going to put that, and we will find that the answer for the first change in the diameter for the outer ring is going to be 98 multiplied by 10 up to 12 minus 5 inches. Now we'll repeat the same step for the inner ring, and we'll find the answer is going to be 222 multiplied by 10 up to 12 minus 5. So we should find that the addition of both should be equal to the maximum interference between the two, the shaft and the hole. If you are going to put that on Excel sheet, so definitely you can find your calculator by simply changing the A, the B, the C, and the D, which is the total interference. Calculate the model, input the modulus of the outside member and the inner member and the portion ratio for both, and then you can put the equations in the Excel sheet. It will give you the P, will give you the sigma O, sigma I, the delta O, and the delta I. So the next video is going to be about the first question we have in our example.